Today, we will study the differentiability of functions of two or more variables. For a function of a single variable, say fx, differentiability of f at x means the existence of the derivative f prime x. This was equivalent to the graph of f having a non-vertical tangent line at x. Now we ask, what's the right concept of differentiability for a function of two or more variables? In a natural way, it must be the existence of tangent plane, but this requires more than the mere existence of the partial derivatives. For example, considering the next function, it is easy to prove that the two partial derivatives exist. See its graph, and obviously the graph has no tangent plane at the origin. The reason is that the graph is not well approximated there by any plane except in two directions. A tangent plane ought to approximate the graph very well in all directions. In order to define the differentiability of fxy, let's recall the geometry interpretation of the differentiability of fx. For fx, differentiability of f at a means the graph of f having a non-vertical tangent line at a. That is, there exists a tangent line through AFA that approximates the function for values of x near a. In other words, f is locally linear at a. Definition: we see that a function fx is locally linear at a if there is a constant m such that the following expression holds, where epsilon h is infinitesimal. By the definition, it is easy to prove that in the one variable case, if f is locally linear at a, then f must differentiable at a, and m must equals f prime a. On the other hand, if fx is differentiable at a, then the following expression holds. Hence, f is not linear. Therefore, for one single variable function, fx is locally linear at a if and only if fx is differentiable at a. The concept of local linearity thus carries over to the situation in which f is a function of two or more variables, and we will use this characteristic to define the differentiability of a function of two or more variables. First, we define local linearity. Definition: we say that f is locally linear at ab if the following expression holds, where epsilon 1 and epsilon 2 converge to 0 as h1, h2 approach to 0 vector. We can simplify the above definition by defining the following vectors: p0 equals ab, h equals h1, h2, and epsilon h equals epsilon h1, h2. Thus, we have the following equation. Now we define differentiability to be synonymous with local linearity. Definition: the function f is differentiable at p if it is locally linear at p. The function f is differentiable on an open set R if it is differentiable at every point in R. In the formula below, the red vector is denote this sign, and it's called the gradient of f. Thus, f is differentiable at P if and only if the next expression holds. The operator is read there and is often called the del operator. In the sense described above, the gradient of fxy becomes the analog of the derivative f prime x. Besides, we point out several aspects of the definitions. 1. F prime x is a number, but the gradient fp is a vector. 2. The products are dot products. 3. The definitions of log linearity, differentiability, and gradients are easily extended to any number of dimensions. Example 1. For the following fxyz, find its gradient at points 1, 2, 0. Solution. By the definition of gradient, we need to compute the three partials. They are sin z plus 2xy, x squared, and x cosine z. At points 1, 2, 0, the three partials have the value 4, 1, and 1, respectively. So, the gradient is this vector 4i plus j plus k. According to the definition of differentiability of bivariate function, we have the following equivalent definition. fxy is differentiable at xy if and only if there exist two constants a and b, such that the total increments of fxy can be expressed in the following form, where a and b are independent on delta x and delta y, and a delta x plus b delta y is called total differential of fxy at the point xy, denoted by dz or df. We know that for one single variable function fx, if it's differentiable at a, then the derivative f prime a exists. Can this conclusion carry over to the case where f is a function of two or more variables? The answer is yes. If fxy is differentiable at xy, then the two partials must exist. Moreover, the total differential of f at xy can be expressed in the following form. Now we prove this theorem. Since z equals fxy is differentiable, so the total increment delta z can be expressed in the following forms. Let delta y be 0, then rho equals the abstract of delta x, and the partial increment equals as a dot delta x plus the higher order infinitesimal. Dividing the both sides of the equation by delta x, we have this term. Let delta approaching 0, we get the limit is a. So, the partial derivative of f with respect to x exists and equals a. Similarly, the partial derivative with respect to y exists and equals b. So, the two partials of z exist and the total differential dz equals a delta x plus b delta y and equals partial z partial x delta x plus partial z partial y delta y. According to the definition and the theorem A, we can determine differentiable lots at some points, say 0, 0, by the next steps. Step 1. Find fx 0, 0, fy 0, 0. Step 2. Compute the total increment delta z. Step 3. Determine the quotient is infinitesimal or not. By theorem A, we know if fxy is differentiable at xy, then the two partial derivatives must exist. But if the two partial derivatives exist, fxy may be not differentiable, such as by the definition of the partial derivative, both fx and fy 0, 0 are 0. At 0, 0, the difference of delta z and fx 0, 0 delta x plus fy 0, 0 delta y is this expression. Now we check if this expression is higher order infinitesimal with respect to row or lots. Consider P1 approach 0, 0 through the direction of 1 equals x. Then we have this expression. So P1 does not tend to 0 with row approaching 0. Therefore, fxy is not differentiable at 0, 0. This example shows that the existence of partial derivatives is only a necessary but not sufficient condition for the existence of the total differential. Now, we will give the sufficient conditions for differentiability. Theorem B. If z equals fxy has continuous partials fx and fy on a disk D whose interior contains xy, then f is differentiable at xy. Proof: the total increment delta z equals this expression. It can be rewritten as the following two terms. For the first term, when y plus delta y is fixed, this difference is the partial increment with respect to x, and fx y plus delta y is regarded as a one variable function about x. Since the partial derivative of f with respect to x exists, according to the Lagrange mean value theorem for derivatives, we conclude that there exists a theta 1 such that this equation holds. According to the continuity of the partial derivative a function fx xy, we have the limit expression. Due to the relationship between function limits and infinitesimal, we get this equation, where epsilon1 is function of delta x, delta y, and as delta x, delta y approach 0, epsilon1 converges to 0. So the first partial increment is expressed in the form. Similarly, the second partial increment is expressed in the form. So the total increment delta z can be expressed in this form. Next, we only need to prove the red part is a higher order infinitesimal with row approaching 0. In fact, the abstract of this term over rho is not larger than the sum of these two terms. As rho approaches 0, the net term tends to 0. So epsilon 1 delta x plus epsilon 2 delta y is a higher order infinitesimal about rho. Then the total increment delta z is expressed as follows. So by the equivalent definition of differentiability, fxy is differentiable at xy. For bivariate function z equals fxy, dz equals partial z partial x delta x plus partial z partial y delta y. Choose zxy equals x, then dz equals dx equals zx delta x equals delta x. That is, dx equals delta x. Similarly, dy equals delta y. So total differential dz equals partial z partial x dx plus partial z partial y dy. Similarly, for differential function with three variables u equals fxyz, its total differential du equals partial u partial x dx plus partial u partial y dy plus partial u partial z dz. Example: for the following function, find its total differential at this point. Note that the two partials are as follows. Substituting x equals 1 and y equals 2, the total differential dz equals 2 times 1 plus e squared dx plus e squared dy. At last, we give the rules for gradients and the continuity versus differentiability. It's easy to prove them. Please complete the proof by yourselves. Theorem C. The Dell operator has the following properties. Theorem D. If f is differentiable at P, then f is continuous at P. Today, we learned the definitions of non-linear, differentiable, gradient, they operate on multivariate functions, and the necessary and sufficient conditions for differentiability, the rules for gradients, and the continuity versus differentiability. Thank you for listening. See you next time.